So this is just going to be a short video that kind of points out some links between the periodic table and atomic orbitals. And so we can use the periodic table that we already know something about, and from that we can come to terms, I think, a little easier with how we're going to identify the orbital type and that sort of thing when we come to quantum numbers. So let's proceed here. So first of all, you do know a little bit about the periodic table. You do have a bit of an idea about certain areas of it. So the first area I'm going to outline here, just going to highlight that component of the periodic table. And we know from previous discussions that that area of the periodic table is known as the S block. And so the S block essentially is comprised of S orbitals. And so when we put electrons into the S block, we're really putting them into an S orbital. So a second block I'm going to highlight is this block, and you probably now remember this block. That block is known as the P block, and so not surprisingly, the P block is comprised of P orbitals. So again, if electrons are going into elements to make up a configuration for a given element they're put into this part of the periodic table, then they're going into P orbitals. Another area of the periodic table you're familiar with, that's what I'm surrounding in green now, and that's the D block, comprised of D orbitals. And finally, the last block on the periodic table then is this block at the bottom, the inner transition metals. And the inner transition metals are that's the F block, comprised of F orbitals. So you've already seen those different blocks, and so there's a pretty immediate link between position on the periodic table and the type of atomic orbital that is going to hold the given electrons. So let's just look a little bit into orbitals. So you've probably come across a definition of an orbital, but here's a pretty simple one. An orbital is basically an area in space where there is a high probability, and that high probability is greater than 90%, of finding an electron. So basically all this means is that an orbital is that three-dimensional space outside of the nucleus where you're going to find the electrons for the most part. Three different representations that I just want to show you here. First one, electron density plot. So basically it just plots electron density versus radius. That's what R is on the bottom, radius. And so this is actually an S orbital. It's a 2s orbital. And so all this is saying is, in that first shaded in area, that first little area in the middle, you have some probability of finding that electron, but the greater probability of finding an electron is in that second shaded area. So that's in this area here. And so that's where there's a higher probability. That's what this is showing, a greater electron density in that region. So that region from here to here essentially is this component on that diagram. And so electron density plots are one way to show where there's a high probability of finding an electron. The second one here is this orbital density picture. This is a little harder to do. It takes a long time. It looks like shading, and it is in fact shading, but all of that shading is done with individual dots. So where there's a greater degree of shading, there's more dots, which translates to a greater probability. What this also shows, which isn't shown in the first electron density plot, are these gaps. So this gap is known as a node. And so you see nodes all over the place. Nodes are where there's no probability of finding an electron, and actually in our first plot, this corresponds to a node. And again, that's that white region where there's no nothing shown. And the last one is something known as an electron contour diagram, and these perhaps are the most familiar in a way because these sort of hard-shelled shapes that we see so often as representing orbitals. And so this particular one that's shown here on the right also shows this node, and the different colors indicate just one or the other areas in that region in space. So those are the sort of some typical representations of atomic orbitals. Like I said, the electron contour diagram, or slight variations in that, are the ones we're most familiar with. So one other thing we do want to come to terms with initially is that electrons or orbitals can only hold 2 electrons at most, and so this gives rise to quite a bit of specificity, and again, from what we know of the periodic table, that's going to help us. So if you look at the s orbital, or the s block, so s block is comprised of s orbitals. Well, we can look at this block and see how wide it is, and it's 2 elements wide. So we go from, say, lithium to beryllium, and then there's nothing, and so we're now moving out of the s block. So if you think about making lithium, to make lithium from the element before it, we add 1 more electron, and we also add something to the nucleus. But the main thing is we add an extra electron. So that electron is going to go into an s orbital. Well, since orbitals can only hold 2 electrons, it means when I go to beryllium, I add another electron to make beryllium. And so this would, in essence, constitute a single s orbital that holds 2 electrons. And that s orbital is now full. And so if I've made beryllium, if I want to make another element that has another electron added, I cannot add it to that s orbital. So that's going to help us in terms of placing things. And so when we look at the different s orbitals, they're all pretty much the same shape. They're all these spherical shapes, but they get larger. And so they get larger because as we move down the periodic table, remember we're talking about increased radius, and so if the radius is getting larger, it stands to reason that part of the reason the radius gets larger is because the orbital is getting larger. But anyways, there's those typical spherical representation for s orbitals. S orbitals hold 2 electrons at most. So again, if we can only hold 2 electrons in an orbital, when we get to a different block, like the p block, we have to have more orbitals. The p block is 6 columns wide. 5 to 10 is 6 columns. That means 6 electrons go across each row in the p block. And that means we have to be able to hold 6 electrons. So every time I go from one element to next, I'm changing the nucleus, but I'm also adding an electron. That electron is being added to the p block, and so I need orbitals to hold those electrons. Well, if the p block is 6 atoms wide, 6 elements wide, and each orbital can hold 2 electrons, it stands to reason I need 3 p orbitals per energy level per row. So I need 3 different p orbitals, and we do in fact have solutions to Schrodinger equation that give us those different p orbitals, and so here they are represented here. And so orientation around that coordinate plane, so this would be known as a px orbital because it's along the x-axis. This would be known as a py orbital because it's along the y-axis, and this is the pz orbital because the orientation along the z-axis. So different orientations in space for the 3 different p orbitals. Notice you sort of put them all together. Again, we're kind of back to a pretty spherical shape, but don't forget all of those put together are 3 different p orbitals, and so that's 6 electrons in there. Finally, we have the D block. D block is 10 elements wide. Rows 3 to 12 is 10 elements, and so we need 5 D orbitals. And so again, when we look at the solution to the Schrodinger equation, we're going to get at our 5d orbitals, and they look something like this. And so again, each of those different orientations in space, now they're getting slightly complex in terms of shape, but each one of those is able to house 2 electrons only. So this is why we have 5 different d orbitals, because we have to be able to put 10 electrons within that d block. And that concludes this quick video on orbitals.